Welcome to orbital hybridization. Learning objectives are explain the process of the hybridization as it employs to the formation of hybrid atoms, types of hybridization and also the importance of hybridization. Hybridization is a phenomenon of mixing of atomic orbitals of different shape, size and energy to form new equivalent orbitals of the same shape, size and energy. Understanding hybridization by the daily life example. Suppose I want to make tea. So the ingredients needed to make tea are water, sugar, black tea and the milk. When I boil all these two ingredients together, having the different texture and color, so I get tea. And every drop of the tea having the same color, taste and smell. So the ingredients of the tea are like the atomic orbitals, whereas the tea is an example of hybrid orbitals. Now look at the shapes of the atomic orbitals. S orbital is spherical in shape, whereas the p orbitals are dumbbell shaped. They are also having the different energies, but when we mix these orbitals together, we get the hybrid orbitals having the same shape, size and energy. These atomic orbitals are just like the ingredients of the tea, which are totally different from one another, whereas the hybrid orbitals are identical to one another. Types of hybridization which involves s and p orbitals are sp3 hybridization, in which the molecular geometry is tetrahedral, sp2 hybridization having a trigonal planar molecular geometry, and sp hybridization having a linear molecular geometry. Now let us discuss the three types of the hybridization in the carbon atom. To understand the type of the hybridization in the carbon atom, first of all we must know about the electronic configuration of the carbon atom. So the electronic configuration of the carbon atom in its ground state is 1s2, 2s2 and 2p2, while in the excited state, one electron from the 2s orbital will promote it to the 2p orbital. As a result, in the carbon atom, we have 4 valence electrons. Therefore, the carbon needs 4 more electrons to complete its octet and become stable. Note that the carbon always forms 4 bonds, either it's in the form of single covalent bonds, double covalent bond or the triple covalent bond. Or in other words, we can say that when the carbon make 4 single bonds, in this case, the type of the hybridization is sp3 hybridization. Or when the carbon make 3 single bonds, or in other words, we can say that when the carbon make one double bond, in this case, the type of the hybridization must be sp2 hybridization. While when the carbon makes 2 single bonds, or in other words, we can say that when the carbon make one triple bond, in this case, the type of hybridization is sp hybridization. So what about the bond angles in this case? So in case of sp3 hybridization, the bond angle must be 109.5 degree and the molecular geometry will be tetrahedral. While in case of sp2 hybridization, the bond angle will be 120 degree and here the molecular geometry will be trigonal planar. While in case of sp hybridization, the molecular geometry will be linear and the bond angle must be 180 degree in this case. Formula to determine the type of the hybridization. We can easily determine the type of the hybridization by using this formula. Number of the sigma bonds or the single covalent bonds around the central atom plus the number of the lone pair of electrons around the central atom. Note that all the single bonds are sigma bonds and only the sigma bonds and the lone pair of the electrons are involved in the hybridization, and remember that the pi bonds are not involved in the hybridization. Here in this lecture, we have not discussed about the lone pair of the electrons, and I have discussed it in another video. So if the total number of the hybrid orbitals are 4, it means that 4 single bonds will be formed here. So the type of the hybridization will be sp3 hybridization. When the carbon or any central atom forms the 3 hybrid orbitals, means it forms 3 single bonds or the sigma bonds, then the type of the hybridization must be sp2 hybridization. And if the central atoms form the 2 sigma bonds or single bonds, then the total number of the hybrid orbitals must be 2 hybrid orbitals, and in this case the hybridization must be sp hybridization. Now let us discuss the type of the hybridization in detail. First, sp3 hybridization. As the name indicates, sp3 means 1s and the 3p orbitals are involved there in hybridization, and as a result we get 4 hybrid orbitals. For example, methane. Look at the Lewis structure of the methane. Here the carbon is a central atom which overlap with the hydrogen, and as a result 4 sigma bonds are formed. We know that all the single bonds are the sigma bonds. So here the carbon is making 4 single bonds, and we know that when the carbon making 4 sigma bonds, so the molecular geometry must be tetrahedral and the bond angle will be 109.5 degree. And the type of the hybridization is sp3 hybridization. Now look at the diagram of the methane. Here 4 hybrid orbitals are present and the bond angle is 109.5 degree. These hybrid orbitals having the same shape, same size and the same energy. sp2 hybridization. As the name indicates, sp2 means 1s and the 2p orbitals here are involved in the hybridization, and we get 3 hybrid orbitals. Here 1p orbital is not involved in the hybridization and it's form a pi bond, and we know that the pi bonds are not involved in the hybridization. Now let us take an example of the sp2 hybridization. Ethene. So here is the Lewis structure of the ethene. Here the carbon is a central atom which forms 2 sigma bonds with the hydrogen atom and 1 sigma bond with the carbon atom by head-on overlapping. And we know that when the central atom or carbon form 3 sigma bonds, in this case the hybridization is sp2 hybridization and the shape is trigonal planar and the bond angle must be 120 degree in this case. Now let's discuss the orbital structure of the ethene. Now look at here in a diagram that the carbon is overlapping with 2 hydrogen atoms, and as a result 2 sigma bonds are formed by head-on overlapping. Whereas on the other side the carbon is overlapping with another carbon atom and another sigma bond is formed here. So in case of the ethene 3 sigma bonds are formed, whereas the pz orbital overlap parallelly, and as a result pi bond is formed here in case of ethene. So the bond angle in this case is 120 degree and the shape is trigonal planar. sp hybridization. As the name indicates, sp means 1s and the 1p orbitals will overlap here to form 2 hybrid orbitals. Here 2pz orbitals remain unhybridized, means they are not involved here in the hybridization and they will overlap parallel to form 2 pi bonds. The example of sp hybridization is ethine. Now look at the level structure of the ethine. Here the carbon is making two sigma bonds or single bonds. And we know that when the central atom makes two sigma bond, the type of the hybridization will be sp hybridization. Here the bond angle must be 180 degree and the shape will be linear in case of sp hybridization. Now look at the orbital structure of the ethine. Here carbon is overlapping with hydrogen atom by head-on overlap and it forms one sigma bond. Whereas on the other hand, the carbon is overlapping with another carbon atom by head-on overlapping and form another sigma bond. As a result, two sigma bonds are here. So in this case, the type of the hybridization is sp hybridization. Now look at the unhybridized orbitals. Here, two unhybridized orbitals which on parallel overlapping form two pi bonds. And we know that the pi bonds are not involved in the hybridization, it forms parallel overlap. So the linear shape molecular geometry will be there in case of sp hybridization and the bond angle will be 180 degree.